Arithmetic.
Logs.
Yeah.
Logs.
Okay, so yeah, quick and close. This is I think this is pretty good day for you to kind of understand logs a little better than maybe you did the first time through. Second time through, it's always easier. So yeah, we're talking about logs. We're going to start off with our discussion of logs. We're going to get there in kind of a strange way, but it'll make sense, I promise you. So let's do a quick review of inverse relations, specifically inverse functions. Let's start with this, okay? So what's our recipe? If I'm giving you a function y equals 3x plus 2, and I want you to write the inverse function down, okay? Let's talk about this stuff a little bit. So this is going to be kind of a combination review of inverses, and then eventually we're going to get to, hopefully, we'll see how far we get. I want to eventually get through properties of logs. I don't know, we'll see how far we get. Short day today. We'll just get as far as we get. How do I calculate an inverse?
You switch the x and the y
Okay.
and solve for
Good, I switch the x and the y and I solve for y. Very good. Okay, so we're gonna flip the x and the y, and that's gonna give us the equation x equals 3y plus 2. What would the two steps be in order to isolate y?
Subtract 2 and
Subtract 2. So x minus 2 equals 3y, divide everything by 3, and I end up with y equals x minus 2 over 3. Okay, good. So if we wanted to write these using function notation, maybe we could do something like, say, instead of a y, let's call this f of x. And instead of a y here, let's call that maybe something like g of x. Now, if these are truly inverse functions, what has to be true if I take a composition of those functions? So if I do f of g of x or g of f of x, what do I have to get back? And this is really crucial. No.
0.
No. X. Yeah. I have to get back x. And this is really, okay, so I'm glad I asked that question because this is something I really want to reinforce. The whole purpose, in a sense, one way of looking at inverse functions or inverse relations at all, even if they're not functions, is they undo each other. That's the whole point, right? So if f of x and g of x are inverses, and by the way, it's not a one-way street. It's not like I'm just saying g of x is the inverse of f of x. If g of x is truly the inverse function of f of x, then f of x is also the inverse of g of x, right? So if they are inverses, then f of g of x has to undo the g of x, and we end up with just an x. And g of f of x would have to undo the f of x, and we'd end up with just an x. If that doesn't happen, then they are not inverse functions, okay? Let's just see it in action. What is f of g of x in this case? What's that looking like? So what's f of, if f of x is 3x plus 2, what's f of g? Well, hold on. If f of x is 3x plus 2, what's f of a?
3a plus
What's f of b?
2, 3b plus 2,
What's f of g?
3g.
Ah, okay. So I'm going to get 3 times g of x, which is x minus 2 over 3, right? Plus 2. Okay, well, what's that give me? 3 times x minus 2 over 3 is just x minus 2, agreed? Because I'm gonna get some cancellation there, right? 3's cancel. And I just, x minus 2 plus 2 is equal to x. It works. Okay? So what's g of f of x going to be then? If g of x is x minus 2 over 3, what's g of a?
X minus a minus 2.
So what g of a would be?
A
Minus 2 over 3. G of b would be?
b minus 2.
G of f would be?
F minus 2.
Plus 2.
Okay, good. So we're going to get f, which was, forgot what f was, 3x plus 2 minus 2 over 3. And if we simplify this, 3x plus 2 minus 2 is just 3x over 3 is x. So either way it works, doesn't it? Okay, so those are inverse functions. Okay, let's try it again. How about something like this? F of x equals x squared. Okay, so what are my steps to get the inverse function?
Switch.
Okay, so probably the first thing is let's write this with a y. Okay, so we'll write the original function as y equals x squared, right? And then we're going to, in fact, let me do this. I'm going to switch this around just a little bit. So we'll write it as a y equals x squared. And then, as you told me, we just switch the x and the y. Right, so we end up with x equals y squared. I'm going to flip that around. Just do it like that. And now I solve, and what do I get?
Y equals the square root of x.
Okay, so y equals the square root of x. And so g of x equals square root of x. Okay? So what is f of g of x then? Okay, everybody see that? Okay, I'm gonna get square root of x squared, and what is that? X. Well, so far so good. What's g of f of x?
X, the square root of x squared.
Okay. Square root of x squared, and what's that? No,
No, just x.
not.
Absolute value.
Absolute value of x. Go on. So are f of x equals x squared and g of x equals the square root of x inverse functions?
No.
No.
They're not. They're not. Here's why. Let's graph them. Let's graph them. If I graph f of x equals x squared, it's that, isn't it? Okay. What is g of x equals the square root of x? It's just that. What are we missing?
The other side.
Oh, yeah, we're missing the other side, aren't we? Right? We're missing that. We're missing the minus the square root of x part. So the math gods were very wise here in a way, because when we solved this, what should we really have gotten here when I square rooted both sides?
Plus or minus.
Yeah, we should have gotten a plus or minus, shouldn't we? Okay, and when we got that plus or minus, why does the word or have to be included there? The math gods are so consistent in their logic that they're really smart about this. If we're starting off with the function, and f of x equals x squared is a function, isn't it? Right? It passes the vertical line test, correct? When I wanted to calculate an inverse of that, they gave me back, well, I really was looking for inverse functions, wasn't I? They gave it back to me. In fact, they gave both of them back to me. Because if I take the inverse of my original parabola, I'm going to get a sideways parabola. Is that a function?
No.
No, it's not. But the math gods are going to give it back to me in small pieces that are functions, in the form of a plus or minus statement, right? Plus the square root of x is a function by itself, and minus the square root of x is a function by itself. Okay? So how could we have predicted, and I know this is just review, but how could we have predicted that our original function was not going to have an inverse that was a function?
This,
How could we have predicted, okay, but there's something about maybe even the graph here, right? Our test for a function is the vertical line test, right? The function y equals x squared, or f of x equals x squared, passed the vertical line test. But what other test could we have applied that would have predicted its inverse would not pass the vertical line test? Okay, hold that thought. I'm going to show you a trick, really good trick. And you might want to, well, I'm recording this, I'll put it in my notes, so maybe you don't want to write it down. If you write stuff down, write it down. If you just don't, that's fine. What's the relationship between the graphs of inverses? Is there any symmetry there? So if I had gone back to my original example up here, and I got f of x is 3x plus 2, and g of x equals x minus 2 over 3. Let's graph those on Desmos real quick.
Yeah, that's what.
And let's see if you guys, just a quick reminder about symmetry here. 'Cause this is pretty important stuff too. Ah, okay, good. Symmetrical about the line, about a line, but it's not, it's an inconvenient line. Right, if we graph the function f of x equals 3x plus 2, and we graph the function g of x equals x minus 2 over 3. Yeah, look, they don't have any obvious symmetry. They're not, it's not rotational symmetry, right? And it's not folding symmetry over either of the x or the y axis. But there is a folding symmetry over the line y, over the line y equals x. Looks like I got something there. Okay? Okay, everybody see that? Okay, so that's the symmetry that we get. That's the symmetry that we get is we get folding symmetry over the line y equals x. And we can see that further even with this more complicated case. And Desmos is pretty useful here because we don't have to, we can graph non-functions in Desmos, which is handy. So if we go down here, we make f of x x squared. And in fact, I'm just going to call that y equals x squared to make this a little bit easier. And instead of writing this as a function, I'm going to write it as x equals y squared. Look, we still have that same symmetry, don't we? Okay, those two relations. Okay, so how can you, just another quick question here, how can you do that? How can we quickly find what the graph of an inverse looks like? Because that's kind of a difficult thing to do. It's counterintuitive to fold or reflect something over a line that's not vertical or horizontal. I mean, if you can do it, then great. But if it's hard for you to do, I got another recipe for you. What are the steps for graphing an inverse? In fact, I'm going to make a new page for this. Doesn't even have to be a function, just graphing an inverse. What can you do? And it doesn't matter which one you start with because they're inverses of each other. Okay, there's two steps you can do that are kind of cool. First step is you can rotate. You can rotate pi halves, or whatever how you prefer to think about it, 90 degrees counterclockwise, so positive direction. And then you reflect over y-axis, and that always works. Okay, so for example, if I start with, who's going to draw this? If I start with the function, okay, let's start with this one. Let's say I start with the function x squared plus 4, something like that. So it looks like this. And I want to graph its inverse. Okay, let's do these steps in order. So step 1 is going to be, I'm going to rotate this thing 90 degrees counterclockwise. So doesn't that mean, what that means is I'm just putting a tack at the origin, I'm spinning the graph 90 degrees. Right, so I end up here. There's step 1. Then if I reflect that over the y-axis, what do I get? I get what I should get, because there's the line of symmetry. Yeah, I could have done it with this one too, though, couldn't I? If I had rotated this guy 90 degrees counterclockwise, it lines up with the via parabola. When I reflected, it stays there. It always works. Okay. That's a good one to remember. It really is a lot easier than trying to reflect over a diagonal line. Okay, back to business. So then, what's the significance of this? Okay, here's the significance. Let's talk about logs now. Let's focus on just don't worry about the bottom part. We'll start with the natural log. So if f of x equals log x, what's the graph of log x look like? Let's graph that. What's log x look like?
Isn't the,
Where's it asymptotic? The negative x-axis, right? So it's coming from negative infinity. It's going to be asymptotic on the negative x-axis, and then it's just going to gradually grow. Well, not gradually. It picks up speed and grows towards infinity, right? Okay, where does it cross the y-axis? At 1, right? And we know that because the log of 0 is 1. Or excuse me, e to the 0. Did I ask you about a log function? I meant an exponential function. Sorry. That no wonder you're having trouble. Yeah. I meant to ask you about, I'm asking you about the function y equals e to the x. Sorry.
oh,
Yeah,
okay.
there we go. There we go. Okay. That's what I wanted to do. Sorry about that.
Okay,
So it comes, so you probably were wondering what the heck I was talking about.
yeah.
And let me make this a different color too. Because I want to save the blue for the log x. So we'll make this yellow. That's what I meant to do. It comes from the negative x-axis and it crosses the y-axis at the point 0, 1, because anything to the 0 is 1, right? And then it increases exponentially, right? Okay, why do I draw that? Well, let's go back and let's talk about our inverses here a little bit. What's going to be the inverse of e to the x? Let's do it that way. Yeah, we can do it that way. That's good. I'm going to try this a little different.
Plus or minus the x.
Let me bail on this page.
It is. I mean, yeah, pretty sure
So we've got
that's what it is.
y equals e to the x, and we want to come up with the inverse. What do we do?
Switch the,
Okay, we just switch the x and the y. Okay. So that's going to give us x equals e to the y. Okay. How are we going to solve for y?
Are you going to look
No, that sounds pretty complicated. Okay.
take the y.
This is, now I want you to
root.
think about something. This goes back to logs. Okay. There's a way of rewriting any exponential statement you can write as a corresponding log statement. Is this ringing a bell?
Yeah,
Okay,
but I
good.
don't remember.
And there's a way you can always remember this. And this, I know it's gonna sound dumb, but it goes back to the log thing here. You can always, a log is an exponent. Okay, that's the way you can always think about this. A log is an exponent. Okay. So if I want to write this as a logarithmic statement, whatever is in the exponent is what the log is equal to. Okay, whatever the log is equal to, a log is an exponent. So y is going to equal the natural log of x, right? Because a log is an exponent. Whatever the log is equal to is what shows up in the exponent of the exponential statement, right? If you were to utter these words at a timber convention, you'd probably get some quizzical looks, but it works in math.
They have timber sports.
Right, okay.
They have
So,
dogs.
but it is helpful to remember that for trying to make this connection. So then, and is everybody okay with that statement? You guys, does that make sense from last year? Remember
Yeah,
that?
yeah.
Those are equivalent statements, right? And another way to remember this, that I think is also really useful, the base stays the same. What's the base of a natural log? Of a natural log?
E.
Base E, so there's an invisible E there. Well, look, the base is the base, right? The base of the log becomes the base of the exponential, right? This is really, we call this a base E exponential, wouldn't we? Right? And this is what we call a natural log is a base E log, as opposed to like a base 10 log, right? Does that make sense? So if we were gonna do something in parallel here with, instead of having a base E exponential, if we started off with like a base 10 exponential, well, what's gonna be the corresponding log statement here? If we were to flip the x and the y, right, if we're gonna solve for the inverse, I would have gotten x equals 10 to the y, right, if I want to find its inverse. And what's the equivalent logarithmic way of saying that?
Y log base 10.
Ah, okay, good. Y equals base 10 log of x. Why? Because a log is an exponent. Whatever the log is equal to shows up in the exponent. And notice that the bases are the same in both equations, right? It's a base 10 exponential and it's a base 10 logarithm. Okay? All right, so that's helpful to us then, right? If I know that x equals e to the y is the same thing as saying y, that's the inverse of y equals e to the x, but that became, when we wrote that as a log, that became y equals the base e log of x. These are the inverses, right? Everybody agree? Because how did we get them? We switched the x and the y and solved for y, didn't we? Everybody agree? Okay. Well then, you can tell me now exactly what a logarithm looks like as a graph, can't you? Right? It's got to be the inverse graph of this. So it's going to have that symmetry about the line y equals x. And so we'll just try to muscle through this one and do it using just a straight reflection. What's this point going to reflect to?
1, 0.
1, 0, right? And how come? Because if I want to map point to point, what do I do to get an inverse? I just swap the domain and the range. Is really all I'm doing, right? So I'm swapping the 0 and the 1. So I get the point 1, 0. And instead of being asymptotic on the negative x-axis, I'm going to be asymptotic on the negative y-axis. So everybody see it's just going to do this, right? So there's our natural log function, isn't it? Okay? Make sense? Okay. So this is really useful to think about the fact, remember the fact that these are inverses of each other. They undo each other, right? Because they undo each other, it allows us to go about this in a little different way now, right? If I wanted to solve for y here, an alternate approach would be, I don't have to rewrite the exponential statement as a log statement. I can always do that, but I could also do something kind of an algebra. I could do some, as long as I'm doing the same thing to both sides, if I'm starting with x equals e to the y, I could take the log of both sides, right? Take the natural log of both sides. The natural log of x equals the natural log of e to the y. But natural log function and exponential function are inverses of each other. So what do they do to each other? They cancel, right? You get that? So this is kind of an algebraic approach to this. We'd see that the natural log and the exponential cancel, and that's just equal to, that's how I can solve for y. Right? Does that make sense? Okay? All right, so if I wanted to, for example, let's say I wanted to solve an equation then. Right? I want to solve an equation. I want to solve this thing for x. Right? how do we,
This one from 0 to 100 really quick.
I mean, how do I do this? Well, I could, if I wanted to, I could always go back and rewrite the exponential statement as a log statement. A log is an exponent, right? So whatever a log is an exponent, so whatever, hang on a second, yeah, so whatever's in the exponent is what we're taking the log of. Let's not do it that way. Let's not do it that way. Let's do this algebraically instead. How do I undo an exponential?
You take the ln of those.
I take the natural log of both sides, right? And so all I'd have to do here is just, I end up with the natural log of e to the 2x squared plus 1 equals the natural log of 7. And the natural log undoes the base e exponential, right? And so I end up with just 2x squared plus 1 equals the natural log of 7. And I'm not going to go from there. I mean, but that's, we would have to just, that's just a number, a very inconvenient number, right? But I could subtract 1, divide by 2, and square root both sides. I'm just going to get some really bizarre, plus or minus, some really bizarre square root. But the point is, the hard part of this was getting it out of the exponent. Okay, what would I do down here if I want to solve this one?
You could raise it all.
Okay, I'm going to exponentiate both sides. I'm going to do a base e exponential of both sides, right? And so I could do this one as e to the natural log of x squared plus 1 equals e to the 3. And what's the point? Well, these undo each other, right? And so I end up with just x squared plus 1 equals e to the 3. And once again, I could, we get some bizarre answer because e to the 3 is just a number, right? And I could solve that if I wanted to subtract 1 and take plus or minus square root of both sides. And I could maybe get a decimal pretty easily with my calculator, right? Okay? All right, so good. So we've got that good quick review, right, of just how is natural log related to the base e exponential function. We do the same thing for base 10 logs. We typically use natural log instead because it makes more sense. It has real meaning in the world, which we'll kind of explore and plumb the depths of why is it such an important relationship when we get into some problems a little bit later on. We can actually look at some calculus of logs that does some really interesting things. Like we could look at, like we'll when we apply this, eventually we'll look at things like radiocarbon. We can understand with calculus, we can understand how we get to those equations pretty easily. Okay? All right, so now next issue, properties of logs. Okay, so we know what logs are, we know what a natural log function looks like, right? We understand that natural logs and base e exponentials are inverses of each other, and so they can be used to undo each other, which is really important. There are some important properties of logs, and we use these a lot in calculus. We're working towards, once we kind of get a little practice taking derivatives of logs, which is where we're going with this, there is a whole technique in calculus that we're going to move towards called logarithmic differentiation, where we specifically are going to take logs of equations to take advantage of their properties. There's a good way to think about this. When I take a log of some arithmetic relationships, meaning products, quotients, or powers, it does something important to us on our order of operations tree. It's always going to move us down one rung on the order of operations tree. Now, we're not going to worry about the parentheses part, but the other parts, exponentiation, multiplication, division, and addition, subtraction. Wouldn't you agree that as we climb this ladder, those arithmetic processes are getting kind of more difficult? Adding and subtracting is easier than multiplying and dividing. Multiplying and dividing is easier than exponentiating. Agreed?
Yeah.
Okay. So look what this does. Do you remember what this property is? What's the natural log of a product of A times B?
The natural log of 1
It's okay. The log of a product equals the sum of the logs. Right? Look what that did. That moved us down a rung, didn't it? That moved us down from multiplication to addition. That's handy, right? What about the log of a quotient? Okay, good, that becomes the natural log of A minus the natural log of B, so again, that moved us down a row, right? Now, what about the natural log of an exponential, natural log of A to the n? What do you do there? Okay, you can pull the n out in front of the log, right? And so we end up with n times natural log A. Well, look what that did, same thing. It took us down from an exponential down to a product, right? So it moves us down a row. But you do bottom out. And so this is only useful if you're trying to sort of untangle a knot, a mathematical knot that involves products and/or quotients and/or exponentials. If the knot involves a sum or a difference, there's nowhere to go. There's no other rung to step onto. So the point I want to make with that is, what if we tried something like this? What's the natural log of A plus B equal to? There's nowhere to go. You can't do anything with it. It is simply the natural log of A plus B. You're stuck. There is no property that applies. And so once you get to the bottom rung, these properties aren't useful anymore. Okay? Does that make sense? Okay? So let's try a couple. What's the, and we could even, one other thing that's kind of interesting. We don't do a lot of proof in here, but we'll just do a real simple one here. It'll be informal. But can you prove to me the second property here from the first and the third?
Yes, but I don't know.
Then the answer is no. But yeah, I have confidence. I think you can. I think you can. What am I going to start with here? The natural log of A divided by B. How could I rewrite that?
Guide me.
Revan, what are you going to do? No, I think you're. I could tell. I could see you got this. You got this. Come on, Revan.
I'm gonna take a pass.
Okay, all right. Now, the only ones that we have, once again, these are the ones that we're starting with, right? Those two. So those have already been proved, Wilson. How could I prove the quotient property? Log of a quotient equals the difference in logs.
Well, it doesn't hurt to try.
What do you think? Just
So B would basically be B to negative 1.
okay, good. We could rewrite this as the natural log of A times B to the minus 1, right?
And the element of B to negative 1 would be negative.
Okay, yes, first we have to do the product, right? So the natural log of A times B to the negative 1 would be the natural log of A plus the natural log of B to the minus 1. And by the exponent rule, I could take that negative out front, couldn't I? Right? Everybody see that? So it's going to become natural log of A minus natural log of B. Okay, make sense? Good. Okay, good? All right, so let's try a couple of these. When are we out of here? Like 11:01?
Yeah.
We'll just get through a couple. Just get through a couple of these. But this is good practice. So what about this? What about this first one?
LN2.
Good. Natural log 2 minus natural log 3. And just so you know, you really don't want to say ln. You'll be in college. You'll be ridiculed for that. You'd say, I don't want to be ridiculed. You'd say natural log. All right. You'd say natural log.
I'm just gonna say LN just as much.
So
Natural log of 1 minus natural log of
Just say LN.
okay, but what's the natural log of what?
1.
No.
X.
E to the
E to the
0. X log.
0.
I mean,
0.
I would say kind of, because it's obviously it would apply to that too, but that's not really an explanation. That's just a statement of, obviously,
There.
yeah.
Guessing.
You have to realize our calculus is also much easier.
But I didn't really, that's not an explanation, it's a statement of, yeah, you can look at it.
We'll call our quits there. We'll get a little more practice tomorrow, and then I'll put an assignment up. Just like a pre-calculus assignment, just getting a little practice with this stuff. I'll put it up today, but we're not done with our review yet.
No, alright.
So then